Okay. Oh.
These are just a few more random graphs that I made. So here I started with a line and then sort of zigged out from that. Turns out there was 15 vertices and 15 edges, and then there's this region inside here, and then the whole region. So that's 2 as well.
So even when you made something kind of really random and complicated, and then you added like a closed region to it, still got 2.
And
All
it
right.
still works. And then there's this one with sort of spirals out and then closes here. So it gives us 15 vertices and 16 edges and 3 regions. Triangle, the sort of spiral, and then the outside.
Yeah. Actually, that one kind of shows that it can be hard to count the number of regions sometimes.
Yep. And then this also gives us 2. So it does seem to be working for every graph we've tried.
All right.
Conclusion, every connected planar graph has the number of vertices minus the number of edges plus the number of regions equals 2.
Yeah. So, but it's interesting with that definition. He has to be pretty precise. It has to be connected and it has to be planar. So what does that mean?
I guess that would sort of mean like it's contained on a 2-dimensional plane.
Okay.
So, like it can't be, like if the graph was 3-dimensional and it was sort of curving up off the page, you wouldn't be able to calculate the regions in the plane because it would come off the plane.
Right, right. And then, so he gives this example, which is a really interesting one.
Alright, so he says, how about this graph, and then it's sort of a square with an X in it. 4 vertices, and then 4 edges are on the outside, and then 5, 6, because there's no vertex in here.
Right.
And then 5 regions, which gives us 3.
Yeah, so what can you then conclude about this graph if now you've gotten 3?
There's some error with it.
Well, not that there's an error. I mean, there it is, right there. That's what it is. It's not an error in it. But what does it fail to meet in our definition? That every connected planar graph satisfies vertices minus edges plus regions equals 2.
Well, I think that involves having every space where edge connects, and an edge connects be a vertice.
Yeah, that's right. That's what we need, where they cross. But it must fail something. If this is true, that every connected planar graph has this, and this one doesn't, it must not meet one of the conditions, or at least one. So what condition does it not meet?
Well, it's on a plane, so it must not meet the connected.
Okay, so what does connected mean?
All of the regions you have to be able to get from any point to every other point.
All right, can you do that?
Yes, here you can do that.
Okay.
So it seems to satisfy the connected part.
It does seem to satisfy the connected part.
Well, except if you count, like, if there's one vertice here that you can't get to from any other point because it doesn't exist.
Well, yeah, but that's not the problem. We know the vertices. There's just 4 of them because we can see them, and we can always get from one to another. So it must not meet the other condition.
So it must not be in a plane. So that means these don't connect. So one would have to go like up over the other somehow.
Right. That's the problem. So you can't have a cross. If this is in a plane, they cross are going to touch, and so there'll be a vertex there. And since the fact that when there's not a vertex there, you can't draw this without these diagonals touching if you draw it in a plane. So this graph, as drawn, would not be planar.
Yep. And so he said you can fix that by either adding a vertex or making this edge sort of loop around to the other edge.
Yeah, so let's talk about the 2 fixes here. So this one, what was the fix here?
So that fixed the problem by putting a vertex where the 2 lines meet.
Yep.
And from there we get 5 vertices and then 8 edges, because these are all split into their own edges, and then 5 regions. That gives us 2.
Okay.
And then the looping around way gives us 4 vertices still. Now we have 6 edges, but 1 less region. So that gives us 2.
Okay. So how can you tell that this graph and this graph are the same? This is kind of the problem that we had yesterday.
So all the other connections are the same. You have the ones are on the outside and then a connection going this way. But then you have this connection going from this point to this point. And then you could sort of create that by looping around along the outside, and that would still keep it on the plane instead of having to go over or under.
Yeah, so we can pretend they're like rubber bands and we can just kind of stretch it over and
Yep.
avoid the crossings. Okay, cool. All right, so let's go to the last pages real quick and see where this left off.